Many security controls apply at the network level, and that's why it's important to understand network switching, its relationship to cybersecurity, and how various configurations can be used to mitigate risk. So network switching, what we're talking about is having a hardware device, that would be the network switch, that allows multiple network connections. So you plug in cables, which normally maps to a patch panel, which in turn connects to different wall jacks throughout an office environment where we plug in things like network printing devices. We can plug in laptops, servers, desktops, basically anything that allows connectivity to a network in a wired configuration. But what's interesting about a network switch is that it has its own memory where it tracks the device MAC addresses plugged into specific switch ports. The reason it does this is because when there is a communication between two devices plugged into a switch, instead of flooding every port with the transmission, only the port with the correct recipient, because the MAC address is remembered, gets sent that traffic. So it allows then, as a result, multiple concurrent network conversations at the same time on the same switch. That's in comparison to a network hub. A traditional hub is one big single collision domain, meaning there can only be one conversation on the network at a time. Because when one machine sends a transmission to another and they're plugged into a hub, that transmission is flooded to every single hub port. That's not the case with the network switch. So you could say then that a network switch maps to layer 2 of the OSI model, the data link layer, because it's dealing with MAC addresses and it determines how devices gain access to the network transmission medium. But the thing to think about is that there are also layer 3 switches out there. So in addition to the traditional layer 2 switch capabilities, they also have built-in routing capabilities, which allows them to map to layer 3. You can route between various virtual local area networks or VLANs. Plus, it's got a MAC address table and an IP routing table. But what is a VLAN? A VLAN is a virtual local area network. With most physical network switch appliances, every port in the switch is in a single VLAN. But in our diagram, our single Ethernet switch, it's an 8-port switch, is configured with 2 VLANs. The first 4 ports shown on the left here are configured in a VLAN that we might use to plug in specifically IoT devices, where we have another VLAN called the accounting VLAN, where, of course, we would plug in accounting stations. One of the benefits of doing this is that you are reducing the overall amount of network traffic. Instead of having a bigger network with a lot of conversations, you have 2 smaller ones. But it's also about network isolation. Whether or not this is a layer 3 switch, if we don't have routing capabilities between the 2 VLANs, then if we had an infected or a compromised IoT device on that VLAN, it might be able, through lateral movement, to discover other IoT devices on the IoT VLAN, but it would not be able to communicate with anything on the accounting VLAN. So this is one way to mitigate risk related to using IoT devices on a network, besides the obvious performance benefits of breaking a large network into smaller ones. And then we have network access control, otherwise called NAC, N-A-C. You'll often see this referred to as the IEEE 802.1x standard. Be careful not to confuse that with 802.11, which generally speaking is the Wi-Fi network communication standard. So 802.1x can be applied to network switches, wireless routers, VPN appliances, dial-in modems, which are still actually in use in some networks. The purpose is that these are endpoint devices that can require connecting clients to first successfully authenticate, usually through a centralized authentication server, before being allowed on the network. So instead of just plugging into a network or connecting wirelessly to a network with no challenge, they can require authentication at various levels, and not just device authentication, even user authentication. So before you even get a valid IP address to participate on the network, you have to prove that you are a legitimate user of the network. Network access control can also be configured with policies that will run health checks against connecting clients to make sure they are healthy. To make sure, for example, that they have an up-to-date malware scanner, Perhaps that they have an endpoint firewall solution enabled, checking that OS and app updates are applied to the connecting device. In some cases, even making sure that certain types of hardware security authentication devices are plugged in before allowing access, for example, to a VPN. So the network authentication process with 802.1x works like this. The supplicant is the term that we use for the client that's trying to connect to the network. So the supplicant attempts a network connection, and in a perfect world, everything is configured using multi-factor authentication, MFA, as it's considered more secure than just username and password authentication, despite the fact that it's not perfect and impenetrable. In step 2, we would then have a radius client. Now that, in this example, would be the network connection point, whether it's an Ethernet switch configured with network access control, a Wi-Fi router, a VPN appliance, whatever it is, that is the client, not the user device. In this context, remember, the user device is called the supplicant. Anyways, in step 2, the radius client, let's say it's a wireless router, will receive the supplicant request to connect to the network, will check against configured policies that we just mentioned, like patches being applied, up-to-date malware scanner being in place, and it will forward that authentication request to an authentication server, which we call a radius server, which is located elsewhere on a protected network. In step 3, the radius server would authenticate the supplicant, and the supplicant is then granted network access, and at that point they would be configured with the appropriate TCP/IP protocol stack settings, like an IP address, a subnet mask, DNS server, a default gateway, and whatnot. Now, what can we do to mitigate risk related to networks in a general sense? One would be physical. Limit access to wiring closets. So wiring closets, server rooms, data center equipment racks should all be locked. In an office environment, any network switch ports, such as wall jacks where you can plug in devices to get on the network, they should be disabled if they are unused, such as an empty cubicle. This is done through configuring the switch. You can also configure network switch port static MAC addresses. What that means is that either you configure the network switch ports so that after the initial connection of a device, the switch will remember that MAC address and it will only allow that device to connect to that switch port. Or you can even manually pre-configure that information for the utmost in control when it comes to network switch port security.